So, hi everybody. First of all, I'd like to welcome you to this talk on performance analysis and optimizations of CAE applications with focus on StarCCM Plus as a case study. Maybe just as a start, a short introduction who I am. I am working as a pre-sales consultant and benchmarker at Science and Computing, Department HPC Services and Software. Before I start, I would like to make a short introduction for the company. So probably most of you, it's the first time you hear the name. Science and Computing was founded in 1989 by some members of the faculty of the University of Tübingen, and since 2008 it's a Bull Group company. It has nowadays around 300 employees in different locations, main location in Tübingen, other locations in Munich, Berlin, Düsseldorf and Ingolstadt. We are mainly focused on technical computing, so it's not only high-performance computing or graphical computing, but mainly on technical computing, which includes every direction of computing, but mainly CAD, CE, and CAT fields. And we count as customers from different directions: automobile manufacturers, suppliers to these manufacturers, manufacturers of electronic components, aerospace companies, manufacturing companies in general, but also chemical and pharmaceutical companies. But we are also active in the public sector, and that scientists for the German Parliament will helping them to port data from different systems into Linux systems. So, as part of our activities or our core competencies, we can name IT services, consulting and software, including software development and software consultancy. We are mainly active in a lot of fields, as you can see here, and I am mainly active in distributed computing and HPC, and as I said before, doing mainly benchmarking and pre-sales. That includes also hardware configuration. Before I really start with the talk, I would like to thank the contributors that helped me in this work, mainly persons in these two teams, application and performance team at Bull, and especially Madeleine and Damien, but also members of the HPC service and software team, especially Joseph and Oliver, which helped me to do the work in a most simple way. Thanks goes to CD Adapco, which was helping us with resources in order to do the tests. So let's start without losing more time. So in this talk I will make a short introduction why we really want to do this work and why we did that. I will describe shortly the benchmarking environment and go into some initial performance optimizations that we did, and then we will jump to the performance analysis and comparison, which will deal mainly with CPU frequency dependency and memory hierarchy dependency, but also we do a simple CPU comparison between two types of CPUs. I also analyzed the impact of hyperthreading when using hyperthreading by overpopulating the nodes, but also the impact of hyperthreading even when we do not use hyperthreading, but it's on the computing nodes. It really impacts sometimes the performance, and in this case we will see the effect. I also did an analysis on the turbo boost. So we can see many aspects of the turbo boost on nowadays CPUs, and I was mainly focused on how we can use turbo boost to reduce costs like license costs, because we usually see turbo boost as a parameter that increases power consumption costs, but there is also another side that you can use turbo boost to reduce the number of cores that you're using on a CPU. In this way you can reduce license costs for such applications. To finalize, I did some MPI profiling just to have an overview of what was happening, and I will conclude the talk with the conclusions that have to be done for this kind of applications. So first, a short introduction. We know that ISV software is in general pre-compiled, so we don't have any more options to optimize the code. And in such case, there are a lot of other options how we can improve the performance for such codes. So in this HPC environment, you have the options that you can tell to the scheduler or the batch system where to put this job. And you have in a system a lot of different jobs, and you have also heterogeneous systems with different types of nodes, with different types of CPUs, with different types of RAM DIMMs, with different types of RAM space, and you really, when you start executing an application, you don't know which one to choose. And that's why you need to do some profiling and some kind of optimization that comes afterwards. Another type of optimization is runtimes. You can do CPU binding. You can place the task in a different fashion that fits to the for a better communication pattern, but also that you improve, for example, memory locality and so on. And there are also some operating system optimizations which I'll talk a little bit later. So the purpose of the study is to analyze the behaviors of ISV application with this, in this case, with focus on StarCCM+, and apply these optimizations in order to improve resource utilization. As a test case, we are using StarCCM 8.02008 and platform MPI 0802, and this is aerodynamic simulations with 60 megapoints. The benchmarking environment is mainly with Ivy Bridge CPUs. The table is so big, I just need to say a few points. These are mainly 10-core CPUs and 12-core CPUs, and on some of these systems the hyperthreading is on, and in some of these systems the hyperthreading is off in BIOS. So the initial optimizations, I guess everyone in this room knows most of the terms, for example CPU binding or turbo boost or hyperthreading. I will not stop in detail in these terms, but mainly for some of you the term zone reclaim or transparent with huge pages might be new, or I need to stop and say some words on that. So zone reclaim is a technique in Linux. I guess all Red Hat distributions have included it now. So Linux, when starts, makes an analysis of the transfer rate between the NUMA nodes. The NUMA node is just a bunch of cores that have the same distance to the memory, which means that in a double socket machine you have two NUMA nodes, and in respect to this analysis that Linux makes, he decides whether to enable or not zone reclaim. And with this assumption, we can say that maybe on some nodes or zone reclaim is enabled, but maybe on some other nodes zone reclaim was not enabled, even though the nodes might be the same type. So Linux decides dynamically to do this. So then we thought we will enable this option by force, so that we have heterogeneous environments in each node, and we can also profit from this feature. Transparent huge pages is also another technique in Linux. I will tell later that maybe in this case did not help so much. This is a very good technique in order to manage a lot of RAM space. So nowadays the nodes get more and more RAM, and you have to somehow deal with that. Let's see the performance improvements that we got when we applied these optimizations one by one. As we can see, let's start with the results on 6 nodes while having 20 tasks per node. We can see that from CPU binding we got a performance improvement from 25%. And when enabling zone reclaim we got 23% in comparison to the last result. And if we go into tests with more nodes, we can see that CPU binding is also is every time very important thing to do. We see that the effect of zone reclaim is not that important anymore when you go to more nodes, and we think that this is coming because of the fact when you have less nodes doing the same type of job, you have more need for memory throughput, you have more data on the node, and probably that's where zone reclaim is helping a lot. And in this node you have more communication, and probably you have more communication going also between the two sockets in the node, and that's why you see more effect when you have tests on less nodes. So, but we didn't stop here. It's a good analysis, it's a good performance result, but we needed to understand really what's going on with the application. So what kind of dependencies this application has. So what we can do to analyze the performance of such applications. First, we can analyze the dependency of the application on CPU frequency or memory hierarchy, including here cache and main memory. But we can also compare different type of CPUs in order to see which CPU is better for this type of application, like 10-core CPUs, 12-core CPUs, and then you have to somehow select the compromise between them. We can analyze the impact of hyperthreading and turbo boost, and we can do MPI profiling. But why should we do that? So the idea is that we can better utilize resources in a heterogeneous environment, and this helps in selecting the appropriate compute nodes. Like we send the job to the nodes that have the CPU of this type, and we can just select the nodes in order to give to this type of job the amount of resources it needs, not more and not less. This is very important in a working environment. Sometimes we need to find also the compromise between performance and costs. In this case, I'm talking about license costs and power consumption. And sometimes we have also to predict the behavior of application on the next generation of processors, like what's coming next. You have more cores, maybe more cache, and so on, or maybe more memory bandwidth, and probably maybe a little bit of more frequency. But yeah, you need to analyze the application in order to say this application will behave like this in the next generation, and which one would be the best one to select as CPU type. So I'll start with the CPU frequency dependency, but first I will explain how we make these tests. So we have done tests on 6, 12, 24 and 48 nodes by running 20 tasks per node, and while changing the CPU frequency from 1.2 to 3, including the turbo boost. We put these numbers in this chart and then include potential trend lines that should mimic the dependency on the CPU frequency in this case, since the CPU frequency is the only changing factor here. And we can see here the exponentials. That means this represents the dependency on the CPU part, but we need to be a little bit of more practical. This is probably including also other minor dependencies inside, but this gives an overview of what's happening, and you get the 85 to 88 dependency on the CPU frequency. But we have to consider that while changing the CPU frequency, you also impact the memory bandwidth, because on the CPU you have an integrated memory controller, and probably there is also some memory bandwidth impact inside this value, but it's just to give you an overview, just in order to select the most suitable CPU for this application. So in order to back up what I just said, we also analyze what's happening with the memory bandwidth when we change the CPU frequency, and we compare this with the speed up. We did tests on 6 and 48 nodes, and we compared speed up and memory throughput increase ratio, and we see that this is almost the same. So you get the same speed up because also the memory bandwidth or the memory throughput also increases. Everything is working faster, the cores are working faster, the caches are working faster, the memory controller is working faster, and if you have enough memory bandwidth, you will get the same ratio. From this chart we can also understand that the memory bandwidth is not the bottleneck in this case, because you always get what you want, and then this is very helpful in such a scenario. And we see the same behavior for 8 and for 6 and 48 nodes. So there is a small gap, but this is to be expected, since on 48 nodes the memory bandwidth requirements or the memory throughput is less, and I will come back to that later. Let's jump to the CPU comparison. We did two kind of tests. We first compare node to node by taking all the cores in each node for two CPU types, the 12-core CPU type and for the 10-core CPU type, and the first results say that we have 8 to 9% better results on the 12-core CPU, but we have to consider that this comes with some costs, like increased power consumption and increased license costs, because you have 2 more cores and licensing is being done on the number of cores. We also analyzed the core-to-core performance by clocking both of these CPU types only at 2.4 gigahertz and running 10 tasks per CPU on both CPU types. And we still see some better results on the 12-core CPU, even though you have the same parameters. And maybe here a question to you all. What do you think, what would be the reason for that? Do you have any idea? So I have some ideas in mind, but
do they have the same caches?
The 12-core CPU has 30 megabyte of cache, and the 10-core CPU has 25 megabyte of cache, so that's 5 megabyte of cache more for the same number of tasks, which is a very good reason that they get better performance. Yep. Maybe another idea? If we look at the internal architecture of these CPUs, the 12-core CPUs has 2 rings that connects the cores in between. This is just a speculation from my side, so there is no commitment from Intel that this is bringing more performance. And you have 2 memory controllers on this chip. But on the 10-core CPUs, you have only 1 ring that connects all the CPUs, and you have only 1 memory controller. So there is some need to do some more benchmarking on this side. So, but as I said, this is just a speculation from my side. But as you also said, the main reason here should be the cache effect. So you get more cache per task, and if the application needs that or uses that, you will get better performance. So this pushed pushed us to make further tests in order to analyze the dependency on the memory hierarchy. So here we came with the idea, oh, what's happening with the cache? So does this application use it, or what's happening with the memory? Does this application need a lot of memory bandwidth, and so on. So we did first the memory throughput analysis, and we measured the memory throughput with Intel PCM tools. It's just a simple tool that measures the throughput from each socket to the main memory on a second basis. This is not too much, but once again it gives you an overview of what's happening with the application. As we can see here, we run tests on 6, 12, 24 and 48 nodes by having 20 tasks per node again. Here I show the memory bandwidth on each socket. We see a small difference between the sockets, taking into consideration that the measurements were done on the first node. So these are the results taken from the first node where the first rank 0 is running, and you probably have more communication from rank 0 in MPI applications. And we can see a small tendency to go down. So like when we increase the number of nodes, we need less memory throughput, and this we think this is coming because of the fact first that the MPI communication increases and you're losing more time in MPI, and the memory links are a bit more relaxed, but also because with more nodes you have also more caches and you don't need to go to the memory if you really can exploit the caches. What we also did, we analyzed how much reads and how much writes we are doing to the memory, and we can see here that most of the time we spend 20% in writes and 80% in reads. So this is something very good for this application, because we know that writes might be a bit more expensive than reads, but this is also another idea that we get from this kind of profiling or benchmarking. What we also did is to analyze the performance when we change the task distribution. We now use 12, 24, 48 nodes, but we just put 10 tasks per node. And on the first scenario, we call it the compact scenario. We put all the 10 tasks on one CPU. And on the second scenario, we put these 10 tasks by splitting them or scattering them 5 to 5 on each CPU. In this way, you give to each task double the amount of cache and double the amount of memory bandwidth, while keeping the MPI communication overhead constant, because you don't change the number of nodes, you just change the number of CPUs being used, so you just change the cache and memory dependency. And here I show the impact on the elapsed time. Then I show the impact on the memory throughput, so what happens, it gets increased or decreased, and the impact on the level 3 cache misses. As we can see on 12 nodes, so this I consider a small number of nodes, we see a reduction in the elapsed time, so let's say 10% improvement. We see an increasement in memory throughput, so let's say these tasks that are now running on separate CPUs are using more memory bandwidth because they have now more memory bandwidth. And we see that we also reduce the level 3 caches by, let's say, 10%. But this is not the same when we go to tests with a lot of nodes, like 96 nodes. And we see that we still reduce the elapsed time by 9%, but we see that the memory throughput did not really increase. And yeah, we see that the impact on the cache misses is almost the same, but what's suspecting here, why didn't the memory throughput increase? And the explanation that we give to this is that you have more caches, and at some point you saturate the memory bandwidth, you don't need more. So you just get this performance improvement, not from the memory throughput, but mainly from the caches. And this backs up the suspicion that we had before why the CPUs are much better. So we have a higher dependency on the cache than on the memory throughput in this case. So if you have a CPU with bigger caches, you will get better performance than if you have a CPU with the same amount of cache but with more memory bandwidth. And in this case, we can decide which CPU to select. Next, we analyzed the impact of having hyperthreading turned on, but while not using it. So we just distribute tasks on the nodes, but we don't oversubscribe the nodes. We just send as many tasks to the nodes as physical cores we have. So we start with 6 nodes, 12 nodes, and 24 nodes, and we really don't see any big difference, but actually there is some small impact, and it keeps increasing while increasing the number of nodes. And really here we don't have any idea why this is happening. I always get people to tell me, please turn hyperthreading off, and I really was telling why. I'm not using it and it shouldn't impact the performance. At some point, this is 1, 2, or maximum 3%, but it impacts somehow the performance, and the question is why. So I really do not have any idea here. I just say that probably it's the OS jitter, the operating system jitter, when you have a lot of tasks, but yeah, while increasing the number of nodes, you increase the number of tasks, and we are having the opposite effect. So the hyperthreading impact reduces the... Does anyone have any idea? Maybe this is just an open question for me. I don't have any other idea. I am doing CPU binding manually, so I'm just telling you put this process to this core. Sorry?
So MPI, half an MPI that you use, right?
Yeah.
Yeah, so you must be figured out from your
So I'm doing CPU binding with platform MPI. So platform MPI knows that I'm using the cores.
Right. Final schedule, over schedule. Oh, we can go.
No.
That's fine, really.
Any other idea? Okay. We can go on. So for me, it's a very strange behavior because, and there are also other techniques that you can turn hyperthreading on the operating system level, but this does not help to hide this impact. So it's something between the operating system and the hardware. So probably when the operating system knows.
Can you explain that whole process one more time? What exactly is
The chart. Yeah.
hyperthreading?
Okay, so I have nodes with hyperthreading turned on BIOS, and I have nodes with hyperthreading turned off on BIOS. This means that the operating system looks on the first nodes double the amount of cores, and on the second nodes the real amount of cores, physical cores. And then I'm running jobs with the same amount of tasks. Let's say on each node I put 24 tasks. So I have 6 cores and I put 24 tasks, 1 task per CPU core. But I can put there 48 tasks, but I'm not doing this here. I'm not using hyperthreading, I'm just running as much tasks as cores. This shouldn't impact the performance. If I compare the results from these 2 nodes. And in the end,
Do you mind to check on the process how the gigahertz of the CPUs are
The gigahertz is fixed.
Is it fixed?
Yes. I fix it manually. So I fix it to 2.4 and 2.6, 2.7. So the idea is that we take this, let's go to this, because here the impact is much bigger. So in this test, so I have 24 nodes and 24 cores. This means I have 24 tasks per node. And I run tests on this node, which has 12-core CPU, but hyperthreading is on. And I run tests on this node with 12 cores and hyperthreading is off. And the result shows that the elapsed time is reduced by 2.7, around 2.7% on the node which has hyperthreading off. And this is what I call a minimal impact. I was told that you could maybe see 10 or 20% impact when you have hyperthreading on, but you do not use it. Any other idea? Yes. Sorry? The application? I think it is floating point, but... No, I'm not in using hyperthreading. This is the idea. I don't want it to help me. The idea is, why does it impact my performance if I'm not using it? Yeah, but I always get this.
Because, for example, the operating system might distribute the scheduling tasks a little bit.
Maybe, but as I said, I'm doing CPU binding. I'm binding each task to each core, and it's running there. I'm checking it.
But your operating system still has to run several daemons.
Yeah.
I mean, 3% is
Yeah.
below measuring threshold.
Mm. Yeah, I said that probably is the OS jitter, so it's an impact from
Lots of nodes, all jittering a little bit for several nano microseconds. Thus delaying it for very large jobs. This jitter is nothing you should consider. Jitter is, in my opinion, something
Okay. Yeah.
I completely agree with your remark, but maybe if you just look at the context switches, maybe you can get a hint if there is something interesting.
Context switching when going.
On the, say on this cores to which you pin your processes, just when you use a hyperthreading core without hyperthreading, it's just about placement of other processes on other threads.
Yeah.
I had large and long-running interface. 1,000 cores, 500 of which were hyperthreading. And trying to have about 15% performance plus.
I'll come to that when I use hyperthreading. This is strange why I'm not using it. This is the idea. There was some Red Hat. I don't remember. It's in one of the slides in the beginning. Why? No. Okay. Okay. Yeah.
I get differences like that for high performance computing for music production on different operating systems when I And I always assume the operating systems.
No, in this case the operating system is the same, but probably there might be some kind of parameter inside that it's different, but it's the same.
But on one time, the operating system operates as you have everything, and the other time. the
Yeah,
operating system
yeah,
operates
yeah,
differently.
this is,
So
yeah, yep.
in my case, that's what I assume.
Okay, you wanted also to say?
Has to do with the fact how binding is implemented. Probably use the API built-in binding,
Yep.
but in different Linux implementations, they use different indexing. So it may affect, like, I'm not sure, it might change indexing. So if they use some libraries like HW logs that aims to, there's also probably different indexing. Should be same exactly maybe, but if it's something else, it may result not exactly.
Okay. Yep.
One simple comment here. Did you run on different nodes? So the tests you did not switch on and off the hyperthreading and you run on the same node. Because
That's the case. We turned off the hyperthreading on the same nodes.
run on the same node, not on a different node. So let's say you run in the
Yep. So this is the same nodes on the same cluster. So the same nodes. It's a cluster with a bunch of nodes, and I'm using the same of them. So probably one time is using.
then you disable. Then you put
So it's the same cluster, and I turn off hyperthreading on all the nodes, but I'm not using all of them. So probably during runs they are using different set of nodes, but it's the same cluster. Maybe we can proceed offline because shouldn't lose so much time. So the other analysis that we did was to do tests on a fixed number of nodes. We just stick to 24 nodes and reduce by 2 the number of tasks among the runs. So let's say we do runs on 24 nodes and 480 tasks by having 20 tasks per node and 10 per core, and then we start reducing by 2 the number of tasks per node, and then we go to this run on 24 nodes with 48 tasks and 2 tasks per node, 1 per CPU. And we measured the CPU frequency, and it turns out that it changes like this. So we go from 2.9 to 3.6. What we do with this reduction of tasks per node, we first allow turbo mode to clock the CPUs at higher frequencies, but we also, as before, we give to each core or to each task more cache and also more memory bandwidth. So we have all the effects here inside the same test. And what we see here is that the elapsed time really increases, but what we want to analyze here is how much compromise we can make and what we want to achieve, so what the customer is willing to do with this feature. So probably this results show that by reducing the number of cores by a factor of 10, the elapsed time increases only by a factor of 6.7. By reducing, I would read that differently, by reducing the license cost by a factor of 10, we lose only 6.7 performance. So this is up to the customer if he decides to use all the cores, part of them, or just 2 of them. Please take into consideration that the license costs are very high. I don't have the numbers, but I was told they are very, very high, and probably this feature could be used in order to reduce the license cost.
the first one here, you have 1 task per core. The first one.
Here,
Yes.
2 tasks per node.
2 tasks per node, but since you have 2 sockets, so 1 task per core.
1 task per socket,
Per socket.
per core.
Yeah, that's per core.
Yeah.
Because tasks run in 1 core. Yeah, and we have seen that actually too. So that's That's how.
And it's interesting you see the change on the frequency. We really measure the frequency. So this is not.
That's true. That's known thing with you don't have a control on the frequency when you have the two bosses active. And if you run one core, you will have a frequency different than if you run all the cores or half of them. So, and the reason is just for cooling reason. So if you have, there are special cases where you could have in this Intel ion bridge, send the bridge and ion bridge. So you could just cool it in a way that you could just reduce that in all cores. But that's in certain cases where you are just over.
But we have also other effects, and probably this application is also profiting from a lot of features, because it's also using the cache that we are giving to each task. So you give more level 3 cache, and you give also more memory bandwidth, and it's not only because of the CPU frequency. So then we analyze when we really use turbo boost and hyperthreading, and see the impact on the speed up and on the memory throughput. So we see that when we enable turbo boost on a fully populated node, we just see the same ratio between speed up and memory throughput increase. So this is like the same thing that we saw before, that if you change the frequency, the memory throughput will also increase. What we find a bit strange is that when we overpopulate the nodes with normal, without turbo boost, and we compare with the fully populated nodes, so here we have double the amount of tasks per node. So we have 2 tasks per physical core. We see a speed up of 8%, but with the memory throughput increases by 12%, and this difference, we say that it's coming because of the eviction of cache data, since we have 2 threads fighting for data. And the same effect is also to be seen when we also enable turbo boost, but still hyperthreading or overpopulating nodes is still enabled. We did also some MPI profiling. I think this is something to be expected. The MPI time increases, and almost linearly with the number of nodes that we use. So that's very normal. What we also analyze is also what kind of MPI calls have been done during the runtime, and we see that most of the time is spent on MPI all reduce and MPI wait any, and we see also a tendency that this is going down while increasing the number of nodes, and the other calls are increasing by in terms of percentage. We can say that we really did not do any MPI tuning. That means we did not really go into MPI all reduce tuning of algorithms that you can select. We probably would get 5 to 10% of the all reduce time, and we also saw 9% of time is spent on MPI file read. So probably a parallel file system might help in reducing this part, because at this one moment we are not using a parallel file system. So to conclude, we can say, the application is depending on CPU frequencies, so a CPU with higher frequency would be better. The application is dependent more on the cache size per core than on the memory bandwidth, but at some point you will also reach the memory bandwidth limit if you have a lot of tasks in one node, especially when you use hyperthreading. Turbo boost is worth to be used only in cases when you don't use all the cores, like as I said, in order to reduce license costs. Hyperthreading has no positive impact on the performance when being used, but also when it's not being used, it does not really impact the performance positively, but it has a small negative impact. Memory bandwidth and latency, so I can say that it's more latency than bandwidth oriented, so you get all the data megabytes per second. And the MPI time increases with the number of nodes. Probably some tuning on the old reduce operations would help here, and using a parallel file system would also help. I would like to thank you and welcome your questions.